First, I want you just to recall the E2 elimination from Organic 1. So in an E2 elimination, what we do is we take our base, just abbreviate that as B minus, then we have some organic molecule with a leaving group, things like chloride, bromide, iodide, tosylates, things like that. And what you did is you labeled the carbon with a leaving group as alpha, the next carbon over is beta, and as long as you have a beta hydrogen, the base will grab the beta hydrogen, send those electrons down between the alpha-beta bonds, and you lose your leaving group. And the net result is we end up with this alkene product. But when talking about this reaction, you probably remember that we said we can't do this with NH2. So the leaving group cannot equal NH2 because it's a terrible leaving group. So what then can we do to make nitrogen a better leaving group in order to be able to get an E2 type elimination? We can do this through a specialized type process known as the Hofmann elimination. Now, when talking about elimination in Organic 1, we talked about Hofmann products and Zaitsev products, where Zaitsev gave us the most substituted double bond, Hofmann the least substituted double bond. Now, while this elimination we're going to talk about is specialized conditions, this is really where that name comes from, because we're going to find that when there's an option, we actually end up with the least substituted double bond. So basically what we're doing in this Hofmann elimination, the whole key here, it makes nitrogen a better leaving group. So for example, let's say we have this amine, and we're going to subject it to the following 3 steps. We're going to use excess iodomethane, silver oxide, and water, and then we'll heat it up. Okay, if we think of the nitrogen as our leaving group, it's on the alpha carbon, here's the beta carbon, and we of course have a beta hydrogen. So we're going to lose our nitrogen leaving group and beta hydrogen, and end up with this alkene product. Then our byproducts are this trimethylamine, water, and silver iodide. So we need to go through the steps here, each of these 3 reactions, and see what's happening in order to get this elimination process to occur. So starting with step 1, This is just a nitrogen alkylation, which we saw when talking about preparing amines. Okay, so here's our molecule. I'm not going to draw the hydrogen in this time, the beta hydrogen. Here's iodomethane, just like we saw before an SN2 reaction. And then, just like before, a base can take one of these protons. Leaving us with going from the primary to a secondary amine. Well, then this will just happen again. We won't go through all the steps. But now we get the tertiary amine. And then it can happen one more time. And we get this ammonium salt. The second part of this reaction comes where we add the silver oxide and water. So let's take our ammonium salt. Just going to abbreviate my 3 methyls. And we react this silver oxide and water. So this step we're going to call an ion swap. Because what actually happens is the silver oxide and water is generating hydroxide, and the silver will pair up with the I minus, take that and form silver iodide precipitate. So it gets rid of the I minus and replaces it with OH minus. So there's our new ion. And finally, step 3 is heating. And by heating, we eliminate. Okay, I'm going to go ahead and draw back in our beta hydrogen. But what you should notice is that we have this positively charged nitrogen species, which is, unlike a neutral nitrogen, a good leaving group. We also have the hydroxide paired up with it. Remember from organic 1, heat favors elimination. So by heating this up, the hydroxide will act as a base, grab the beta hydrogen, and eliminate. There's the alkene product, plus water, and and trimethylamine. Now in this case, it was pretty straightforward because there was only one type of beta hydrogen to eliminate. But if we have multiple types of beta hydrogen, we can potentially get multiple products.